All right, good morning. Here we are. It is June 27th, 2016, and here we are for another exciting day of ENGR 2301 Engineering Statics. Joy. How exciting. I bet all of y'all were just, all weekend long, we're just like a kid before Christmas, just saying, I can't wait to get back to statics class. I don't know how can I get through a day in the summer without statics class. It's just, you go to bed on Friday or Saturday night just completely unfulfilled, just feels off, just didn't have statics today. Anyway, so some bits of business we have again for the class in Houston. The exam is tomorrow. For the class in Tyler, the exam is this evening online. And then on so we'll have lectures through the rest of the week. On tomorrow and Wednesday we'll cover centroids. On Thursday and Tuesday, next Tuesday, we will cover various topics of moments of inertia, and that's it as far as lectures go. So after that, we only have the final. Today we're going to go through a couple practice problems review a couple homework problems from the Beer Vector Mechanics book. And then we are going to have some more notes on shear and bending moment diagrams. All right, so let's begin. So problem 7.2 in the Beer Vector Mechanics book. Determine the internal forces, axial, shear, and bending moment at joint J of the structure indicated. And frame and loading from problem 6.78. Okay. So we need to find the forces on this member here. We need to find the internal forces on the member there. And in order to do that, we would first need to have the reactions. In order to find the internal forces, we'll first need to find the reactions. Okay. So again, we have this will be a bit of a review on reactions as well. We will have, well, actually, let me draw this as an exploded free body diagram. I think that'll be a little bit clearer than trying to do this on there. So we're going to have member ABD. Again, I'm going to be looking for the reactions and the joint forces on member ABD. So we're going to have member ABD, A, B, and D. Then we'll have member ACE, A, C, and E. And then we will have member BC. Now, let's see. So I'm going to have AY and AX. And normally, if this was at any other angle, I might be tempted to say that this is I might be tempted to say that this joint force is an X and Y component. But I know because this is a pin-pin member that its force must act directly along the axis of the member. Therefore, this is only going to be, I'm only going to put BY here, just for simplicity's sake. And then I'm going to have DX and DY. And finally, EY. Then I will have the 450-pound force here. And I will have the 450-pound force here. And then here I will also have what you might call CY. Which force is 300 pounds. Oh, 300 pounds? Yes, sorry, that's 300 pounds. Sorry about that. 300 pounds. Other questions? Yes.
Also, this isn't that important. I think that's EX.
EX. Oh, thank you. Yes, EX helps if you label the correct letters. All right. moving right along. Okay, so I'm going to get dx and I'm going to get dx, dy, and ex via the global free body diagram. And let me show the forces on the global free body diagram. So again, this is the exploded view showing 3 local free body diagrams, like so. And then I guess here I would have a corresponding, if I really want to be proper, I'd have a corresponding CY and a corresponding BY here on the vertical piece. Although we're really not, really don't care about that for this. Okay. So I'm going to have EX, DX, and DY. And now I will use the global free body diagram to solve for the reactions at D and E. Reactions, actually maybe I'll write up here. Reactions at global free body diagram, I should say via global free body diagram. Okay, so I'm going to first do the sum of moments about D, and that will let me have EX. That gives me EX times the distance of 6 feet plus 300 pounds times a distance of 12 feet plus 450 pounds times a distance of 4 feet. All of this is equal to 0, and then EX will be negative. EX will be equal to, let's see, so 300 times 12 plus 450 times 4 divided by 6 is equal to negative 900 pounds. Negative 900 pounds. Now, let me just underline this section. Sum of forces in the x direction, it's going to be dx plus ex equals 0. Therefore, we can see that dx is positive 900 pounds. And via sum of forces y, oh my god, that looks terrible. Sum of forces in the y direction on the global free body diagram, I will get that dy must equal 750 pounds upward. 750 pounds upward. Okay. And then, so I have this one and this one, and now I need, I'm going to do I don't really care about, let's say, well, we'll get it, never mind, we'll be fine. Now I'm going to look only at the free body diagram of member ABD. From free body diagram of ABD. Well, the first thing I'm going to do is a sum of moments about point A. A sum of moments about point A. And what that will do is I will have BY times a distance of 8 feet plus dy times a distance of 16 feet minus dx times a distance of 6 feet equals 0. And from that, we can get that, yeah, let me go ahead and replace these dy and dx with their actual numbers. Let's see. So dy has a value of 750 pounds. And dx has a value of 900 pounds. So we have the 900-pound dx generating a negative moment about point A. The 750-pound dy will generate a positive moment about point A. And that looks good to me. Okay, 750 times 16 minus 900 times 6. And from this, I will get that by is equal to, then divide by 8. I got negative 825 pounds. Negative 825 pounds. Okay, so negative 825 pounds. Like so. And now, let's see. So we have by, we have dy, and dx. We can get ay and ax simply via a summation of forces. Yes, summation of forces in the x direction. I will have ax plus dx. Please silence electronic devices. Equals 0. And from this, I will get that ax is negative dx, or negative 900 pounds. Negative 900 pounds. Summation of forces in the y direction will give us ay plus by plus dy equals 0. And from this, we can get that ay is equal to negative by minus dy equals negative 825 pounds minus the 750 pounds. And from this 825 minus 750, I get 75 pounds. Any issues with this so far? So positive 75 pounds. Any questions on this? Again, I'm just, yes?
In the first, over there, you made the sum of forces equal 0, but you didn't take
Over where?
sum of forces on the y direction. You just
Which one?
right there, where that one.
Uh-huh.
There was no ay or by.
Yes, this is the global free body diagram. And all I just said was from the global free body diagram that dy is must be equal to 750 pounds. Okay. All right. So I'm going to need this one. Let me just go ahead and put little circles around the things I'm going to need. So I'm going to need this thing here. I'm going to need this one. I'm going to need this one, and this one. Questions on any of this so far? This isn't the final answer.
Forces along A to D.
Yeah, again, what I'm doing here is I am finding all of the external forces on member ABD, and from that I'm then going to find the internal forces in member ABD. Okay? All right. So now it gets a little tricky. This stuff, everything here is a review from the previous material, but now things are going to get a little bit tricky. So I'm going to keep this, and I'm going to copy this, and this is actually a fairly long one, so I might even give myself a little more room to work than normal. Okay. So let me mark down some of this stuff. Let me transpose this over here. So AX is negative 900. What is AY again? I can get it. Positive 75, right? BY was negative, right? BY negative 825. Thank you. DY or DX was 900 positive. Thank you. And DY is 750. Yes. Yes. Thank you. Will keep me from bouncing back and forth. Thank you. And pounds all around. Okay, so what I want to do next is I would like to translate these into forces that are, say, in order to do this, member forces are always determined along the local axis of the member. Member forces are always determined along the local axis of the member. Okay? So let me show you what I mean by that. See, when we talk about members, we're talking about shear, moment, and axial force. But these are forces along the member's own axis, like an x prime axis. So in other words, over here, if I show you some axes, yes, we have the global x and y axis, but then along the member is the axis we're really interested in this problem. So we want like an x prime axis and a y prime axis. We want the axes that are along and perpendicular to the member. So in order to find the internal forces, I want to draw a new free body diagram, ideally with this member on the horizontal. I'm going to try to redraw a different free body diagram, taking forces along the x prime axis. And in order to do that, first I'm going to need to do a little trigonometry. So let's do that. So I want to get this angle here. Well, that's not too bad. So let me call this, let's just say this is alpha. You know what, let's go ahead and label this alpha. And alpha then would be equal to the inverse tangent of 6 over 16. Sorry, you may be asking, wait, is she actually finding angles? She's actually finding angles for once? Yes, in this case, I will actually find the angles. I think just looking at this, I have a hunch that might be a bit better on this case, but you could probably do it using ratios as well. But just looking at this, for some reason, I feel that I have a hunch that this might be better to do using actual angles, but either way should work. So, you take an inverse tangent of 6 over 16, opposite over adjacent, SOHCAHTOA. And I get 20.56 degrees. So what does that mean? What does that tell us? Well, I know that this is then 20.56. I know that this here is 90 minus that. So 69.444 or 69.44 degrees. Correct? And then this one here, if we need it, I don't know if we will, but if we need it, we have it. This one is, I'm just trying to get all the angles here. 180 minus that. Actually, yeah, that's fine. Let's see. Well, this one, we have that same triangle, right? And so this one is 20.56. Just trigonometry. and this one is 69.44. And again, I'm going to use these simply to determine the, you'll see. Okay, so this one is going to be 900. I'm just going to put all the external forces on here. 900, 750, and then negative 825, or let's draw it as downward, 825, and then let's say that's 975. 75. Okay, so now I'm going to draw a nice big free body diagram of member ABD. Because what I really want to do is, remember in the previous examples, or in the previous lecture, we had these nice horizontal beams, and it was really easy to do a sum of forces and things like that along there. That's what I want. I'm trying to transform what we have here to something with a nice horizontal beam that I can very easily find my axial and my moment and all that kind of stuff. So that's what I'm going to do. So I'm going to draw it like so. And now I'm going to just simply, I'm simply going to draw all of the forces along there with their angles labeled. And I'm going to draw a nice big one so you don't have any problems. And we can all be happy. Okay, so A, B, and you know, I might even make it a little bigger. That's too small. Make it nice and big. We'll draw beams, happy beams. Well, that's not a very happy beam right there. Whatever. Oh, derp, sorry. That's not good. I need to watch more Joy painting. Okay. All right, anyway. A, B, and D. And then we'll end up cutting it at joint J somewhere. Oh, did I just lose my notes? Oh my goodness, sorry, crap. Or did I just go to the next page? No, I actually lost my notes, dang it. Sorry about that, let me just rewrite that. I do need that. Oh man, that went really bad, sorry about that. AX 975, negative 825, 825, 900 and 750, and 750, and then my angles. This was 20.56. This was also that. This here is 69.44 and 69.44. Okay, so let's figure this out. Now, let's see. If this is 29.56, then this one from here to here has to be the 69.44. So, oh, okay, let me just go ahead and save this so I don't accidentally erase that again. Now, look here. So what I'm going to do is I am going to draw a 75-pound force, £75, 75-pound force here, and at an angle of, oh, let's see, of 22.56 degrees. Oh, thank you, sorry, 69.44. 69.44 degrees. And then I will have the this one here, the 90 pound or the 900 pounds, at an angle of well, let's see. This is 69.44. This is 90. So that should just be 20, 20, right? Plus 90. Yep. Okay. So this one here, off of the negative x-axis, is 20.56 degrees. 20.56 degrees. Next, let's see. I have this By force, and this here is coming out like this in relation to this beam, 825 pounds. And the angle on this is going to be 20.56 plus 90, or we can think of this as this, or I'd probably just take this off of the negative x-axis. So this would be 69.44. And then, let's see. I'm going to have, let me erase this because I don't, nope, it's stuck there. I'm going to have, so let's think here. This is 69.44 to the vertical, which means, let's see, so trying to, this one's a little tricky to think through. So this is, from this is like, oh, let me think about that. This is something like, it has to be something like this, right? At 750 and 900. So it's, the devil of this is just working through the trig, really. 750 and 900. And let's see. So I know that I know that from here to the vertical, or no, actually from here so from here to the vertical line is my 69.44, 69.44, which means from here to here, actually from here, this is 90 obviously here, and from here to here is my 159.44. And finally, this one from the x prime axis. Again, what I'm really just trying to do is I'm trying to get all of these with their angles from the x prime and the y prime axis, or mainly just from the x prime axis. And this one is going to be my 22.46 degrees. 22.46 degrees. And this one is going to be my 69.44 degrees. All right, and now we have something cool. Yes? oh sorry. Now we have something very useful. We have transformed all of the forces into forces and angles along the x prime or the local axis of the member. And this is what will allow us to get the shear and moment and axial force at point J. And I am going to do that simply via the method of cuts.
It should be 20.56, right? Not 22.46.
Oh, did I write that down? Sorry, that's 22.56, sorry.
20.5.
Yeah, 20.56, sorry. The same angle as before. Basically, these are all like complementary angles of each other. 20.56 degrees. Although, truth be told, I don't think we're going to need that joint, but that's okay. I just wanted to have it for completion's sake. Now, I do need to find the length of this member, and I will need to find the length of the member along. I need to find basically this dimension and this dimension is what I really need. So let's work through more trig. So let's do that. I need to get a few hypotenuses. Let me just draw this out. In fact, I might, on this next panel, I might copy this just to work on the hypotenuse, because I just need a little more room. I don't want to save my work for there. Okay, so on this slide, I'm only going to work on finding the hypotenuse. I want to find all of the distances along here. So let me say, yes.
Do you have to find the moment in the new axis? Can't you just use the old axis?
I suppose you probably could, yeah. It should be the same. But in order to find moments in the new axis, I need to find my lengths and such. Okay. But anyway, let's do this here. So ABD, ABD, I cannot talk, I'm clearly drunk. ABD is going to be equal to the square root of 6 squared plus 16 squared, which comes to 16 squared plus 6 squared. I get 17.088 feet. Then the rest of this I can just do through similar triangles. That was the key. So AB then must be to 17.088 as 8 is to 16. So AB must be simply that over 2, or 8.544 feet. And then ABJ over ABD over 17.008. So again, all I'm doing is a bunch of rudimentary geometry class material. 12 over 16, so 3/4 of the total length, or 12.816. 12.816 feet, as shown. And then I can simply say if I need BJ, that is going to be equal to 8.854 minus this, or 1/4 of the total length. So that is then 4.272 feet, and JD is also the same. Also equals 4.272 feet. Any problems with that trigonometry? Yeah, you could have just divided by 4 and things like that, but I still needed to use the Pythagorean theorem to find the original length. And okay, just trig stuff. So then I will write this down as, oh, let me put the, I need point J on here, because that's the point that I'm going to take a cut at. J. And that's going to be the point of our cut, so I'll just mark that with a little orange cut. Let's see, and then let me go ahead and put the dimensions on here. So this here is, again, the 8.544. And this is 4.272 and 4.272. 4.272 feet. Okay, now I'm going to draw this cut at J, and I'm going to show all the internal forces on that member that can be on that member at that point. Yes. Yes. This is specifically asking for a point. The question is how to phrase your question. You don't always have to cut a particular point. If they're just asking for a general Freebody if they're just asking for a general shear and bending moment diagram, you will have to choose what points to cut at, and usually solve in terms of X or something like that. If they're asking for a specific point, yes, you can find the internal forces by just a cut at that point. But if you are asked with finding the overall shear and bending moment diagram, you'll need to cut it at multiple points, and you'll need to figure out where to cut it based on where there are discontinuities in the beam. So on this particular one here, I would need a cut somewhere between A and B, and I would need a cut somewhere between B and D to find the entire shear and bending moment diagram of this beam, simply because there are discontinuities here, here, and here. And the discontinuities represent the boundaries of the regions that you could integrate between. So I cannot integrate this all the way from A to D. I can integrate it from A to B or from B to D, but I cannot integrate all the way across because there is clearly a discontinuity in the middle there. Okay. So let's keep moving. Here at joint J, I have a cut here, and I'm going to have some forces on here. So I'm going to have, let me call this NJ, the axial force or normal, the force normal to the member's axis at point J, and your book may use a different notation. I'm going to have VJ, the shear at point J. And notice the direction. I drew it such that it is positive shear according to the sign convention that we saw last time. See, again, positive shear will have an upward arrow on the left and a downward arrow at the right. And then moment MJ will be here. Okay. Could I have done it from J to D? Yes. I could also do it from J to D. Would you? I mean, either way is fine. I could do it from A to J or from J to D. Either one is perfectly fine. Yeah, I don't have to reverse the sign convention. I would just draw the other corresponding piece and reverse the directions of things. But yes, as long as we believe in the equations of statics, as long as we still fear Newton's ghost, I mean, this is still going to turn out all right. I love that phrase, fear Newton's ghost. Anyway. Now, even more ironic is if we say fear the ghost of Einstein. He would not have appreciated that. Okay. 75 pounds. And so each of these is going to have basically an x prime and a y prime component. 900 pounds. And then the 69.44 pounds. And let me show you, let me write the angles. Oh, sorry, 825 pounds. This is 825 pounds. This is 69.44 degrees. 69.44 degrees. And 20.86 degrees. All right. Now the rest is just equilibrium. Sum of forces in the x direction. Maybe I'll just say the x prime direction even to make it extra clear that we're talking about a local rather than a global axis. Sum of forces in the x prime direction. You know what? And I'll go ahead and label this even. Out of this, I'm going to have the x prime direction, or x prime axis, and the y prime axis. And then, let's see. So I'm going to have negative, actually let's say positive, I'll start from left to right, I guess. Or actually, I might need more room than what I have here. Let's write this over here. So I'm going to have negative 900, I need to write my summation again. So summation of forces in the x direction, or the x prime direction, is going to be equal to negative 900 cosine 28.6, or sorry, 20.86. Huh? Oh, did I write that? Or yeah, I'm sorry. I'm having all sorts of transcription errors today. .56, 20.56 degrees. The dangers of doing problems extemporaneously. 20.56 degrees plus 75 times the cosine of 69.44 degrees minus 825. This is, my lines got lost. That's 4 degrees. Minus 825 times the cosine of 69.44 degrees plus nj, and this is equal to 0. And from this, I will get that n at j, the axial force at point j, is a whole bunch of math. 900 times the cosine of 20.56. Let's see, plus 75 times the cosine of 69.44 minus 825 times cosine of 69.44. And I get that nj is equal to 1,1106.04 pounds positive or tension. And that would be one of my 3 internal forces. And barring any math errors, that should be the solution. Okay. Now, let's see. I'm going to try to cram my sum of forces in the y direction over here. So kind of running short on space here, sorry. Sum of forces in the y prime direction is going to be equal to 900 sine 20.56, 20.56, plus 75 sine 69.44, minus 825 sine 69.44, minus Vj equals 0. And from this, the shear at J I can get, so 900 times the sine of 20.
It's negative 900, I think, right?
No, I don't need to put a negative 900 here because I already took care of that due to the drawing them here, just the way I drew them.
Oh, okay.
So 900 times the sine of 20.56 plus 75 times the sine of 69.44 minus 825 times the sine of 69.44. And I get, let me double check that, 900 sine of 20.56 plus 75 sine of 69 minus 825 sine 69, and I get Vj is negative 386.2 pounds. So it's going to be a negative shear at that location, assuming we mathed correctly. Which, after all this work, there's a possibility there's a slight math error in there, but who knows. Okay, but it should be all right, hopefully. Now, I'm going to do a summation of moments. Oh, how about point, maybe A. Summation of moments about point A. And I'm going to try to cram it down in here. Summation of moments about point, not point J, point A. I could do J, but I want to do A. Any point is fine, just some are simpler to solve than others. Summation of moments about point A. I'm only going to need the vertical components of this because the horizontal component is not going to generate a moment through A. The vertical component will generate a negative moment about point A. So, well, first let's just add mj, then minus 825 sine 69.44 times a length of 8.544 feet. And then, let's see, the Vj is going to actually be going, I drew it downward on when I assumed positive shear, but it's actually negative shear, so it's actually going to be going upward, and it's going to generate a positive moment. So I'm just going to go ahead and do that. Plus 8.544, it's that 12.816. 12.816. Actually, let me go ahead and put the force first. So plus 386.2 times, so 386.2 pounds times a distance of 12.816 feet, 12.8 feet. All this equals 0, and I'm really cramming this down in there. And mj, therefore, the internal bending moment at point J is going to be equal to negative 825 times the sine of 69.44 times 8.544 plus the 386.2, 1, times the distance of 12.8 feet. And then that comes to, I got exactly 1,650 pound-feet for the moment at J.
Where did the X go, or was the X talking about the distance?
Was the X talking about the distance? Which one?
This is 386.2 times X times 12.8.
Oh, this is just, sorry, this is just a time sign.
Oh, okay.
Sorry, that's not an X, that's a time sign. Okay, again, so these are the internal forces at point J. So again, my overall method, what I did was, first I found the reactions, or the external forces on the member that are going to be applied to the member. Then I transformed those forces such that they are along, so I had their angles along the local axis of the member. And then finally I just did a summation. I did a cut at J and did a summation of forces there. Alternately, you know, another way to do this is I could have gone back here, and at this point here, I could have cut this and drawn my NJ, VJ, and MJ, and then transformed those forces into the global coordinate system. Either one would work. You either have to convert one to the other or the other to the one, whichever you prefer. Yes.
So on the exam, could you put J on ACE? So it's just horizontal.
Could you put J on ACE? What?
No, I'm just saying to make it easier to put on the exam.
Oh, okay. I don't know.
Yeah.
All right. Okay. Other questions on this? So just a simple problem, right? Well, only took like 5 minutes, right? Okay, it took better part of an hour. Okay. All right. So let's see. Ooh, this is a fun one. Isn't this fun? I'm having fun. Yep. Yes. Okay. Oh, for number 7.2? No. Oh, excuse me. Okay. So 7.43, assuming the upward reaction of the ground on WAB to be uniformly distributed and knowing that P equals WA, draw the shear and bending moment diagrams and determine the maximum absolute values of shear and bending moment. So this is an interesting one in that we're going to do a shear and bending moment diagram for, well, one for something that's supported by the ground in a uniform reaction, and the other, we don't know any numbers. It's all in terms of W and A. Isn't that lovely? Okay, so let's do that thing I said. All right, so let's take a crack at this. Right off the bat, the first thing I'm going to do is to say that, okay, I'm just going to write this as WA, just to get rid of the P. Now, okay, so what does this look like? What do you think this is, a free body what do you think this might be a free body diagram of? Not just that, not a floor. Close, though. This is a building foundation. This is a building foundation. And if you study civil engineering, you will take courses in geotechnical courses, yes. Foundation design courses. You can either take it at the undergraduate or even graduate level. That's always fun. You don't want to take a graduate level soils course? Oh, okay. But it's oh so much fun. Okay. Then, okay, so how are buildings actually supported? They are supported by well, it depends on the foundation. You can have mat foundations like this. Well, actually, it's hard to, it's hard to tell what this would be. But you can have different types of foundations. You can have some are like, sometimes you have things like large footings that are like this, and they're supporting a beam via a large area. Sometimes you just have large, broad mat foundations, this is what most of the houses around here are, just slab on grade foundations, reinforced to a variety of degrees. Sometimes you see beams built into them, things like that. Or you can use things like deep drilled piers. You use these if you really want a stable structure or if you have really bad soils, things like that. And these are supported by a point force at the end and skin friction along their outsides. But anyway, that's neither here nor there. But they all have the commonality that they're supported by distributed loads like this. So one thing I'm going to do now is I recognize that it says there is a uniform upward load on this thing. There's a uniform upward distributed load. And when I do that other one, that makes it look non-uniform, so I'm just going to do this. A uniform upward distributed load. And, well, since I already have I would normally just, if I was going to solve for this, I would normally call this W, but we already have a W. So I'm just going to temporarily call this WU. And let me find what that is. I want to find the value for WU, the upward force. So I'm just going to do a sum of forces in the vertical direction on the global. Let's see, we'll have 2 WA downward. That's these ones here. Minus WA, this one here. And then plus WU times 4A. Again, W is going to be a distributed load, not a point load. So its value, the overall force it will generate will be WU times the total length of 4A. And all of this has to equal 0. And let's see. So A, hey, what do you know? A cancels out. That's nice to know. And so negative 3W plus 4WU equals 0. WU is equal to 3/4 the main W. And we'll never see the letter WU again. I just wanted to quickly get rid of that. Now I'm going to draw the free body diagram. I'm actually going to use. So across the entire bottom, I am going to have 3/4 W. W. I'm going to have in the middle a point force WA, and then I'll just have W. Now, if I wanted to be really proper, I would actually draw these lines so that the number of lines was proportional to the loading, but meh. W. And W. Here. W and W. And then the dimensions, well, of course, are just A, A, and A. Looking at this, how many cuts am I going to need to make? I'm going to need 4 cuts because we have 4 zones, or actually I should say we have 5 discontinuities. I have discontinuity at each end. Then I have a at each of these, I have a sorry, I have a discontinuity at each end. Here I have a discontinuity where a point load, or sorry, where a distributed load terminates. Here I have a discontinuity where a point load is applied. Here I have a discontinuity where a distributed load begins, and here I have a discontinuity where a distributed load ends. So discontinuity, I have 5 discontinuities, which means I will have 4 cuts. The cuts, the discontinuities are the boundaries between the cut zones. All right. So let's do that. Yes.
Spend more time. So the 5 discontinuities are before the first load, after the first load, where the point force is applied, and then the other 2 before the other load. Okay.
Okay. So I am going to have, I'm going to label cuts. Normally I like to use A, B. Well, we have A, C, D. Let me say this is O, F, G, H, and I. These are not necessarily halfway in between. They are just at some point along. Okay. Now, let's continue. So let me do cut F. Right now, cut F. All right. So let's see here. So now I am going to have, when we consider this, so we have this beam. Now, would you believe me if I did this? I don't like this color. Would you believe me if I labeled this as such? Just a second. If I just labeled this as W over 4. Because remember, if you remember, W is a distributed load. And look in this range here. We have an upward 3/4 W and a downward W. So on net, we have a W over 4. Okay? On net, we have a W over 4. And this is not taken at, this is taken at some dimension X here, some dimension X. And I could draw the normal force on the member, but I realize that that's going to be 0, so I'm just going to not draw it. I'm just going to kind of ignore it. Let's see. I want to label my points. This is point A, and this is point E. And then this thing as drawn is not in equilibrium, so I'm going to show my forces on here. I have M, E, and I have downward VE, shear at E. Okay? And so the summation of forces here in the Y direction, I will have W over 4 times X minus VE equals 0. And actually, let me put this over. Let me move this. This is a little bit cramped here. Summation of forces in the y direction, I will have negative W x over 4 plus VE equals 0, and VE is equal to then just WX over 4. Wait. Oh, sorry, that's a negative here. So it's actually going to be a negative shear. Negative WX over 4. All right, that's VE. So I'm going to sort of cordon these off into different zones. Divide my workspace up a bit. Now, let me take the cut G. Cut G, which is right here. Let's see. Oh, I'm an idiot. I didn't find the ME here. I need my moment here. Derp. Sum of moments about, let's say E. I'm going to sum the moments about point E. I will have ME, the actual moment at E, plus W over 4 X over 2 moment arm. Again, the equivalent point force will have a total value of Wx over 4 and a moment arm of x over 2. So ME, therefore, and all this equals 0. So ME is equal to, let's see, that looks like negative WX squared over 8, I believe. Negative WX squared over 8. All right. So we have that, and we have that. And then here, I'm going to have cut G is at, so I'll have A, C, but we will not have the force at P because we're just having some point G here. And the force is on here. It will be drawn in like this. We'll have the upward force. I cannot combine these into a single force now. I could only do that here for simplicity. But now they're covering different areas, so I can't get away with doing that. So I have this upward force of 3/4 W. I have this force of W from A to C. Questions? Yes.
Is E between A and C?
E is a
The first cut?
E is not a cut. E is this point here.
Right. So
F is
on
between A
your
and C.
so on your Freebody diagram for the first cut, what's the boundary on the right?
It's point. Oh, sorry. That should say point F. Sorry about that.
Okay.
That should say point F. Sorry about that. Okay. Sorry about that. So 3/4 W down here, W here, and then I'll have the forces. Let's see, dimensions. I need to actually go ahead and put the. Again, I'll assume upward or positive shear just because. VG. Oh my goodness, I totally messed this up over here, didn't I? They should all be F. Sorry about that. F. Yeah, this all this stuff should be VF, MF, etc. VG and mg, like so. Then I am going to simply say the sum of forces in the y direction is going to be negative w. Oh, let me put the dimensions on here. This dimension here will be a. This dimension will be x. Yes.
So since W is not over the whole thing, you can't do like you did before. Just okay.
Yes, I can't do it. Although I can't combine the loads together because W is not uniform across. Because the distributed load is not uniform across. Sum of forces in the y direction is going to be equal to negative WA plus 3/4 W times X minus VG equals 0. And therefore, VG is equal to, let's see, that's going to be, what's that going to be? If I bring this over here, it's WA, so it's actually just going to be 3/4 WX minus WA, I believe, right? Oh, no, it's not a subscript, that's a multiplier. It's a
Why is it WA?
W times A is the question. Why is it WA? It's WA because it's this distributed load. This is a kips per foot or a pounds per foot. I need to multiply it by a distance to get my actual an actual force in pounds or newtons. Then a sum of moments about point G is going to be equal to negative W. Actually, yeah, we'll do about G. So first I'm going to just have mg plus WA times a distance. Okay, this distance here must be x minus a times a distance of WA is the equivalent point load of this, and its location will be right in the middle of that. So a total distance of x minus a plus a over 2. X minus L? X minus a over 2. Oh yeah, so yes, all this does come to x minus a over 2, yes. X minus a over 2. But yes, obviously that comes to that.
When you said the sum of the forces in the y direction and minus WA, are you talking about the point, the distributed load on top, right?
This one here is the point load of the distributed load on top. This one, 3/4 WX, is the equivalent point force of this bottom one. Okay? Plus WA times that, and then finally, let's see, I need to do this one here, minus 3/4 W times X times X over 2. That's the moment generated by the bottom force. Over 2 equals 0. And mg equals, just, I could express this as this, x minus a over 2 plus 3 wx squared over 8, and we continue like such. Okay, I don't think I'm going to work through the entire problem. I think that kind of gets the idea across. You just keep making cuts at each of the boundaries, then you plot it, you find the maximum value by taking the first derivative in a zone if you wish to, or I guess you don't need to take the first derivative, sorry, you just find the maximum value, and that's it. This is one that might actually be easier to do by inspection, but we haven't yet learned how to do that, yes.
So for the second term, why'd you add a over 2 there?
Why did I add a over 2?
Yeah,
This?
x minus a plus a over 2.
X minus a, because that's this distance. Again, there's a lot of questions about where this thing came from. What is this? Okay, WA, has an equivalent point force right in the middle here. Okay, we're talking centroids here. And the distance between that is the distance from C to G plus 1/2 of the distance from A to C. So that the distance from here to here is A over 2. That's this A over 2. X minus A is the distance here. And that's it. All right, other questions?
This gives you F and G, you still have to do H and I.
Yes, you would still have to find the other two. I don't think we quite have time to work all the way through it, but that will give you the general idea. Yes. We could take advantage of symmetry, but you'd need to know a bit more. Yeah, that would actually work. You could plot it and then mirror. You could simply mirror the plot. But yes. Well, actually, you got to be very careful with that because it's not simply a mirror. For example, what I mean by that is you cannot simply mirror it because, for example, if you have seen already, if you have the classic example is a symmetric, simply supported beam with a load W on it. If you have a load like that, what does this look like? Well, let's see. Say this is length L. I'll show you how to. This is done via inspection. I'll show you that later. That's what we're going to go over today. So the load here is WL over 2. WL over 2.
Which is your favorite method of
Generally inspection, if I can.
Okay.
So this is your load. Then V is going to look something like this. We're going to start up at WL over 2. Go down a total of WL, end up over here at negative WL over 2. And then M. The area of this is L over 2. So then 1/2 base times height, 1/2 WL over 2 times L over 2 is WL squared over 8. And the moment is like this. WL squared over 8. So this is a simply supported beam with a uniform loading. And notice the moment diagram in this case is symmetric, but the shear it's more of a rotation than a reflection. So you will have positive shear on this end and negative shear on this end. But anyway, okay, let's go take a quick break, and we'll come back and look more at shear and moment diagrams by the last method, which is by inspection.